Hey there, Calc 2 folks, back here with some motion into a new direction here in our study of calculus, where we are moving now up into Chapter 12 material, where we're going to be looking at some different ways of defining space and different ways of defining curvature within that space, and looking at some specific cases or different cases for what we might say are ways that we have of defining some what are going to become common curves that we encounter in space. We are going to, in Chapter 12, introduce ourselves to parametric equations, right? Their curves and the calculus involved with parametrics, as well as introduce ourselves to polar equations and their respective, what are known as polar curves, and all the calculus related to those. And finish up the section looking at a particular, what we might say is family of curves in two-dimensional space known as our conic sections. Where all of this material in Chapter 12 really is a bit of prep for what we're going to start off with in Calculus 3 and topics that we're going to need to be familiar with in Calculus 3. All right. What we will see in Calc 3 start to develop is the idea of a vector-valued function. And vector-valued functions are nothing more than really parametric equations organized into the form of a vector. Chapter 13 is where we're going to start our vector study. And in addition to that, in our calculus study, we are going to be looking at regions of space, 2 and 3 dimensionals. And in the two-dimensional context, we are going to encounter regions in space that are what we might say appropriately defined within the polar coordinate system. So there's going to bring out some polar context there, and those ideas of polar equations and the polar coordinate system are going to come into play. And then another idea that also is going to come up in Calc 3 that this Chapter 12 is helping us prepare for is we are going to have to start to look at multidimensional surfaces that exist maybe perhaps, well, to begin with, in three-dimensional space, where to help us understand those surfaces, more specifically to help us understand what we're going to develop as what we call the quadratic surfaces, we're going to want to be familiar with what are called the conic sections. The cross sections for these quadratic surfaces are often going to take on the shape of a conic section. And we want to be able to recognize our conic sections both equationally and graphically when we encounter them within those descriptions of multivariable surfaces. All right, all stuff that's preparing us for this adventure into Calc 3. So, folks, you do want to pay attention to these ideas. These ideas are going to come back into play. They are looking at different ways of defining space here in Chapter 12. All right, and as noted, we are going to start with parametric equations and curves, right? And what I help to do to facilitate, or I take note on to facilitate this study of parametric equations, and that comes to the notion of motion in n-dimensional space requires a way of defining position in space in terms of some additional parameter, using what is known as a set of parametric equations. All right? And this set of parametric equations producing what is known as a parametric curve in n-dimensional space, right? Producing a parametric curve in what we might say is n-dimensional space. All right? This leads us to the definition of a parametric curve in 2 dimensions, right? We're going to spend our time really focused here in 2-dimensional space. We have yet really to extend ourselves into the 3 dimensions yet. But in 2-dimensional space, in R sub 2, or in 2 dimensions of real space, a set of parametric equations describes position given by the xy coordinate using some additional parameter. Right? In 2-dimensional space, what you are going to see is a set of parametric equations define location at x and y in 2 dimensions using some additional variable or parameter value, we say. Oftentimes that parameter value is the value we call t. So if we let t be a parameter, right, our set of parametric equations is going to be given by this set of functional relationships here, right, where we think of x being itself a function of that additional parameter t, and we think of y, right, as being itself a function of some additional parameter t. If we define location x and y as these functions of t, right, we are then defining location x and y in 2 dimensions, right, in terms of some additional parameter t. All right? And the graph here of these relationship between x, y, and t, right, illustrates what's known as a parametric curve, right? The graph illustrating a set of parametric equations over given values of the parameter is known as the parametric curve. And orientation in this curve, right? You'll often be asked to orientate your parametric curve. Orientation in this curve is highlighted by arrows indicating the direction of increasing values of the parameter. All right. If we consider an example of a parametric curve, right, we might consider the set of parametric equations for parameter t greater than or equal to 0 given by this set of parametric equations here. In this case, this set of parametric equations defines location of x as the linear function 1/3 t minus 7 and defines the function of y in terms of t as the linear function 3 minus 2t. These locations of x and y in 2-dimensional space are being defined by these 2 linear functions of t. 1/3 t minus 7 for the case of x of t, and 3 minus 2t for this case of y of t, right? We stated in general in our definition, right? To begin exploring, right, how these locations at x and y behave, right, over values of t, right, we can actually use a table of values. Here we again note x of t is equal to 1/3 t minus 7. Y of t is equal to the function 3 minus 2t for values of the parameter t in this interval from 0 to infinity. This is for values of t greater than or equal to 0. And to begin exploring these, we can look at a table of values, where if I bring that table of values into view here, right, what we're going to note is we are going to be dealing with a 3-column table. What we might say is independent variable in this table is going to be the value of t, right? T can vary independently, right? Whereas the values of x and the values of y that come together to describe this location in 2-dimensional space, they become functions of t. They become dependent upon that independent value of the parameter, right? We can notice here that if our parameter of t is 0, x would be negative 7 in value given by this equation, and y would be 3 in value given by this equation. If t was 3 in value, right, we would see x is given by negative 6, and this value of y would yield negative 3. If t was 6, x would be negative 5, and y would be negative 9. If t was 9, x would be negative 4, and y would be negative 15, and so forth, right? One way to begin exploring the relationship seen in a set of parametric equations is actually to look at a table of values, right? This value t, the parameter t, is going to highlight the independent variable value in the relationship, whereas the values of x and y, those are going to highlight our dependent values and what they describe as a location in space. All right? To further illustrate this relationship, we could form its corresponding parametric curve and highlight some of the orientation on that curve. Here is the corresponding parametric curve in this case. All right. For this set of parametric equations given above. All right. You will notice here at the value of t equal to 0, we are at this location in three-dimensional space. We are at an x value of -7 and a y value of 3. Right? That is this location at t equal to 0. We are at -7 for x and 3 for y. Where here must be our location for where t equals 3. There we're at -6 for x and -3 for y. Here must be our location where t equals 6, right? And so forth. And we can see that this parametric equation does produce, or this set of parametric equations does produce this parametric curve that is linear, right? It does produce this linear curve that starts at this location in space and continues off in this direction, highlighted by these arrows indefinitely, as t starts from the value of 0 and increases along the way. All right? The arrows in this graph highlight the orientation of this parametric curve. They highlight the direction where we see increasing values of t here. Right? This being the location at t equal to 1, this being the 3, 6, 9, 12, and so forth. Right? This graph illustrates the parametric curve, right? Or in this case, the parametric line for this given set of parametric equations, where we are interested in this behavior for x and y for values of the parameter greater than or equal to 0, for values of the parameter starting at 0 and heading up towards infinity. All right? Now, let's bring a note into play here. Note, you could go on to consider also what would be the corresponding linear relationship being illustrated here between variables x and y, right? What we do have here, by having x relate itself to t and have its y relate itself to t, there is an underlying relationship between these values of x and y. Right? And what we do see in the illustration here is that underlying relationship for x and y is itself linear. Where to explicitly find that relationship, we could take note of the following. Right? To begin with, right, since x equals 1/3 t minus 0, this implies t is equal to 3x plus 21. All right? If we go back into this relationship, we are told initially that x is equal to 1/3 t minus 7. Where if I spend a moment using algebra to solve for the value of t, if I add 7 to both sides and I multiply both sides by 3, I will end up finding that t would be equal to 3x plus 21. And furthermore, since y is then equal to the value 3 minus 2t, and t is equal to this value 3x plus 21, we're able to substitute into this relationship for this value of t, the value of 3x plus 21. And we can prepare this value, y equals 3 minus 2 times the quantity 3x plus 21. Implying, if I simplify this expression here on the right-hand side, that 3 minus 6x minus 32 would be equal to y, or y in the end would be equal to negative 6x minus 39. All right? And what we might go on to point is the relationship between x and y illustrated by this set of parametric equations. Well, yeah, by the set of parametric equations over, we might say, values of parameter t greater than or equal to 0, right, is given by, again, we know y equals negative 6x minus 39, where we should go on to point out for values of x greater than or equal to negative 7 in value. Right? Notice the set of parametric equations we have given above do describe this line here that inevitably would have a y-intercept at negative 39, right, highlighted by this equation, it's y-intercept, and has a slope of negative 6, meaning it drops 6 as it runs 1, right? And we do see that happening. We drop 6 and run 1, drop 6 and run 1 as the consistent slope of this linear equation, right? So the relationship between y and x is, going to match up here with y equals negative 6x minus 39, but it's not for this entire line. It corresponds to portions of this line where t is greater than or equal to 0, which you notice in terms of x then would have to be where x is greater than or equal to this value in negative 7. This parametric curve forms for values of x beginning at negative 7 and heading off to positive infinity. All right? But nonetheless, what we do see here is we do get a rectangular description of the relationship between x and y, right, for these values of y that does correspond to the parametric equational description of the curve given above. Right? What we can note is this case, right, illustrates what we call a linear parametric curve in R2. Right? Note, the previous example illustrates what we call a linear parametric curve in R2. Right? In general, a linear parametric curve in the xy plane, R2 space, right, can be summarized by the following set of parametric equations. Right? Right? For the following set of parametric equations, I should say 4 parameter t, right? And that set of parametric equations being x equals x null plus a times t, and y equals y null plus b times t, where t plays the role of the parameter, x null and y null, right? They're going to play the role of a coordinate in space, an xy coordinate, that occurs at the value of t equal to 0. And note here, if t equals 0 in either one of these equations, the plus a term or the plus b term will turn into 0, leaving behind just x null and y null. So those would be our locations of x and y where t is equal to 0. And we'll have a slope described by this, ratio of this multiple of t given in y by b over this multiple of t given in x, the value of a. Right? And notice this does fit the form given above. We can note this equation fits that form. The minus 7 is our x null. The positive 3 is our y null. And what we can see down here in the table is that negative 7, 3 are the values of the coordinate, the location in the two-dimensional space where t is equal to 0. And positive 1/3 and negative 2 here describe the slope of these two parametric lines, right? The negative 2, we might say, describes b. The 1/3 describes a. And if we take, back down here, negative 2 and put that over a in value, which is 1/3, this will become negative 2 times 3, which does equal negative 6 in value. And that was the slope that we found above for this, what? A linear relationship. All right? So in general, all right, set of parametric equations assuming this form where both x and y themselves assume the forms of linear functions of t, parameter t, you do have a overall parametric description that is also linear. Right? Where the constant values in those linear functions in terms of parameter t do form the location in space where t is equal to 0, that corresponds to where t equals 0, and these values of the slope in these parametrical these linear functions of t given in our parametric description, right? They do form into this ratio b over a that describes the slope of this parametric relationship. Now, another common example of a parametric curve we encounter, right, with a little different behavior than a linear curve, is that for the case of what we call a circular parametric curve, which can be stated in general for parameter t as follows here, right, as illustrated, where in this case x could be said to be equal to h plus a times the cosine of t, and y could be said to be equal to the value of k plus a times the sine of t, right? Where the coordinate x comma y equal to h comma k, the coordinate given by this value of h and this value of k, right, would be the location for the center of this parametric circle, right, with the radius measurement r equal to this value of a, seen as this multiplier times the cosine of t and the sine of t, respectively. All right? In this case, if you note the corresponding relationship between x and y, it can be determined explicitly as follows. All right? This set of parametric equations does imply that when we think about the cosine of t, if we were to solve for the cosine of t, we would subtract h and divide by a. We would have x minus h divided by a equal to the cosine of t. And if we were to solve for the sine of t, we would subtract k and divide by a. We would have y minus k divided by a equal to the sine of t. All right? To begin with, this set of parametric equations does imply that the cosine of t is equal to this ratio, and that the sine of t is equal to this ratio. Where we know that if I have the cosine squared of t, and I add that to the sine squared of t, that must be equal to the value of 1 through our trig identities. And it follows then from the cosine squared t plus the sine squared t equal to 1 that if I substitute this quantity into this statement for cosine t, and I substitute this quantity into this statement for the sine of t, I will prepare the left-hand side of this result. I will have x minus h divided by a squared plus y minus k divided by a squared all equal to 1. Where, take note, the squared value on each of these factors, or terms I should say, will distribute to the numerator and denominator. You will have x minus h squared over a squared plus y minus k squared over a squared all equal to 1. Or that you could solve that by moving the a squared from what would be the left-hand side in the denominator of each of these terms by multiplying both sides by a squared to produce x minus h quantity squared plus y minus k quantity squared equal to a squared. This would be the corresponding rectangular relationship between variables x and y that is being stated here implicitly by this set of parametric equations. And what you should note is that this generic rectangular equation corresponding to this generic set of parametric equations for a circular parametric curve, right, is just the equation for a circle, right? The equation for a circle that we should be familiar with from our study of algebra, right? It is a circle whose center is at the coordinate h comma k, right, and whose radius measures a in value. Right? If we were to look at a specific example, right, we might consider the parametric equation, right, given by x equal to 2 cosine t, y equal to 2 sine t, for values of t in this closed interval from 0 to 2 pi, for values of our parameter from 0 to 2 pi. Right? If we were to look at this behavior in a table, we would see that cyclic behavior appear in a table, right? That circular behavior appear in a table, right? For different values of t from 0 all the way back up to 2 pi, the values of x and y will cycle, right, through the noted values seen here in the table, right? We will cycle, as we see here in the table, which would also be illustrated with that cyclic behavior seen in our graph. The cyclic behavior illustrated in the graph would resemble this, right? Starting here at t equal to 0, we'd be at the location 2 comma 0. This would be our location at t equal to pi over 4. This would be our location at t equal to pi over 2. Here's 3 pi over 4. Here's pi. Here's 5 pi over 4. Here's 3 pi over 2. Here's 7 pi over 4. And then finally, this is again where t is equal to 2 pi. And then that cycle just repeats itself again. Right? This set of parametric equations illustrates cyclic behavior. Right? We see that cycling through these x and y values that corresponds to cycling around the circle in two-dimensional space. Right? If we were to derive the rectangular equation for this set of parametrics, right? For this set of parametrics, this does imply that the cosine t equals x over 2 and the sine of t is equal to y over 2. Dividing both sides by 2, we can draw those results. Where, since we know that cosine squared of t plus sine squared of t is equal to 1, it does follow then that replacing the cosine with x over 2 and replacing the sine in this statement with y over 2, we can prepare x over 2 quantity squared plus y over 2 quantity squared must be equal to 1. Or that x squared plus y squared must equal 4. X squared plus y squared equal to 4 being the equation, right? The rectangular equation for a circle centered at the origin with a radius measurement of 2 units, right? And that's exactly what's described here by this set of parametric equations, right? We can see that our center is highlighted by the values of h and k in this equation, which are the constants of 0 in each case, right? Being added to a cosine t and a sine t, where a in this case is the value of 2, right? H and k corresponding to the location of the center, and 2 corresponding to the radius of the circle. All right? So again, I do finish with that. I take note, this result is the description of a circle centered at the origin with a radius of 2, as illustrated above in the parametric curve. All right? So folks, again, this is just the beginnings of parametric curves. All a parametric curve is in two-dimensional space. is a description of location given for x and y in terms of some additional parameter t. The graph that's produced in two-dimensional space then for this parametric description is known as a parametric curve, where we do want to highlight the orientation in this curve. One thing you will note is if we go back to this picture here, I do have these arrows in my graph illustrating that we cycle around the circle in this direction. That is the orientation of this parametric curve. All right? This being the graph for this set of parametric equations. All right? Similarly, we can see back in this picture these arrows pointing in the direction of forward orientation. Right? Increasing values of t. Right? But all we are introducing in this first set of notes is what it means to be a parametric equation in two-dimensional space and its corresponding parametric curves, as well as that skill of being able to go back and derive the rectangular description, folks. All right? Take note of those skills. I do have a few more things to come back and look at with respect to parametric curves, though, and parametric equations. What we want to come back and look at is some of the calculus ideas. So I'll be back shortly to start with that material. I will see y'all then. Hey there, Calc 2 folks back here with just a bit more on parametric curves, where we can take note that these parametric curves certainly do form curves in space. At times those are lines, at times those are circles, at times those are other descriptions of position, right, that are not lines or circles, right? They become just curves in general, where there is going to be a way to find the slope of the line tangent to that parametric curve, or what we might say is the slope of the parametric curve at a given point. Right? And that is the first bit of note that I do set up here is that calculation. I say here, consider the following set of parametric curves, right? Given in general as x equal to x at t and y equals y at t, right? X and y being these two generic functions of parameter t, right? The slope of the line tangent to this parametric curve at the value of t equal to t null, right, is given by this value we understand as dy dx. In the parametric context, slope of the tangent line or slope of the curve is still understood as rise over run, the change in the y values over the change in the x values, right? This understanding of slope, right? Rise over run, change in x, or y over change in x. This ratio is our understanding for slope, where that does not change, but to calculate it using these descriptions of x and y given above, we do take y's description, right, y of t, evaluate its first derivative at the value of t null, and put that over what is going to be x's first derivative in terms of t, evaluated at t null, right? The slope of the line tangent to this set of parametric curves given above is really just the derivative of the function of y in terms of t over the derivative of the function x in terms of t. And we see that in our general statement down here below. dy dx is just dy dt divided by dx dt, or it is just the derivative of y with respect to t times what would be the reciprocal for what is the derivative of x with respect to t. All right? Now, if we put that into play, right, let's consider the behavior for the slope of the tangent for the parametric curve represented by this curve here. All right? X equal to 5t plus 2, and y equals t squared minus 2t. All right? In this particular case, we will note that x at t is equal to 5t plus 2, y at t is equal to t squared minus 2t, and what we're going to need up above in their slope description is the derivative of these two quantities. The derivative of 5t plus 2 is simply 5, right, coming from the first term. And the derivative of y with respect to t is going to be 2t from the first term minus 2 from the second. All right. Note, again, x prime at t is going to equal 5. Y prime at t is going to equal 2t minus 2. So the slope of the line tangent to this parametric curve with respect to t is going to be given by the ratio of 2t minus 2 over the value of 5. All right? dy dx is simply going to be 2t minus 2, the value of y prime at t, divided by x prime at t, this value of 5. All right? And if we consider that behavior over different values of t, one thing we will note is that it does equal 0, first of all, to begin with, at t equal to 1. Right? If I plug t equal to 1 into the numerator up here, it will make that numerator 0. And if this numerator turns into 0, then this entire quantity dy dx would be equal to 0. Right? Implying there that the slope of the line tangent to the curve at t equal to 1 is horizontal. Right? And the slope of the line tangent to this parametric curve at t equal to 1 is, right, is 0, we'll say, illustrating a horizontal line, right? That would be the location where the slope would be horizontal. Start a new sentence here. At t greater than 1, then, if you were to think about t values equal to 1 is where we're going to see the slope be 0, being this horizontal line. At t greater than 1, the quantity 2t minus 2 will then be greater than 0. And if this numerator is greater than 0 divided by this value of 5, which is also greater than 0, will imply that dy dx is greater than 0. Right? And the slope of the lines tangent to the curve at t greater than 1, right, will all be positive in slope. Right? And at t less than 1, that quantity 2t minus 2 will then be less than 0, right? Making this numerator negative in value, and a negative divided by a positive is always negative, right? dy dx will then be less than 0, right? We'll come down here maybe and say, so the slope of the lines tangent to the curve at t less than 1, right, will all be negative in slope. Right? And in fact, we can see that behavior if we were to look at the parametric curve, right, as well as the illustration of dy dx with respect to t. All right? If we look at those two descriptions, here's our parametric curve, right, in space. Here's the location on the curve where t equals 1. Right? Down here is that location. And at that location, t equal to 1, down here, right, we would see the slope of the line tangent to the curve would be horizontal. Right? And the curve's orientation does indicate that it's moving forward in this direction. So to the right of that would be where t is greater than 1, and to the left of that location on the curve would be where t is less than 1. And we could see that the behavior of the slopes tangent to the curve at all these locations where t is greater than 1 will all be positive in value, as highlighted above. And for the values of the slopes tangent to the curve where t is less than 1, we would see them on the left side here where they would all be negative in value. Right? All that being described here by this description of y with respect to x written in terms of t. Now, again, you can analyze actually the graph of this to see the analysis given here above. Right? To see this analysis, we could examine the graph of dy dx with respect to t. And that is the graph I have right here. Right? We are highlighting the behavior of dy dx, 2t minus 2 divided by 5, which is a linear description, over these values of t. And what we notice is over these values of t, we do equal 0 for this value. When t equals 1, we are less than 0, right? When t is less than 1, and we are greater than 0 when t is greater than 1. All describing the slopes of the lines tangent to this curve seen here. All right? If we look at another example, all right, we might consider the behavior of the slopes tangent to this parametric curve. X equals the cosine t, y equals the sine t. All right? You might recognize this curve as being, again, another case for a circle centered at the origin with a radius of 1. This is the description of the unit circle, right? Parameterized in terms of parameter t. What we will note is that x prime's first derivative is negative sine t, and y prime, the first derivative of y, would be sine, for sine of t would be cosine of t. And if we put the y prime value over the x prime value, that will produce negative cosine over sine t, or what we understand is negative tangent of, negative cotangent of t. dy dx would equal negative cosine t over sine t, which equals the negative cotangent of t. This function here in terms of t will describe the slopes of the lines tangent to the curve parameterized here. Right? And as we said, that is the unit circle there, folks. We could break down that analysis, as I do here in a paragraph. Right? What we would note for the cotangent of t, right, at the values of pi over 2 and 3 pi over 2, the numerator is going to equal 0, implying that's where we're going to have tangent lines that are 0 in value, or 0 with slope of zeros, indicating horizontal lines at those locations. When t equals 0 or pi, the sine of t in the denominator would be 0, implying that the slopes of the lines tangent to the curve there would actually be undefined. Where if we inspect the graph at those locations, we will see that's where we will have tangent lines that are vertical in behavior. For then values of t between 0 and pi over 2 and pi and 3 pi over 2, dy dx will actually be less than 0. We will have negative slopes of lines tangent to the curve. And on the intervals from pi over 2 to pi and 3 pi over 2 to 2 pi, we will also see slopes that are greater than 0. Right? Looking at the graphs of both this parametric curve and the description of those slopes, we will see this described behavior above. Right? Here is that curve. Here is our location on that curve, parametric curve, where t equals 0. Right? And we can see as we move in the positive direction, right? Starting at 0, this would be pi over 2, pi, 3 pi over 2, and back to 2 pi. And at 0 and pi is where we would have vertical slopes of the lines tangent to the curve. At pi over 2 and 3 pi over 2 is where we will have the horizontal slopes of the lines tangent to the curve. From 0 to pi over 2, and from pi to 3 pi over 2, we will have negative slopes, right? And from pi over 2 to pi, or 3 pi over 2 to 2 pi, we will have the case for positive slopes. All summarized by this graphical description of negative cosine of t with respect to t. Right there, right, we can see that we are having two cycles of this cosine function from 0 to 2 pi. Oh, sorry, that should be the cotangent function in there. Make sure I have to go back and make that correction. I will do that. All right. In fact, let's do that right. So there, folks, we did correct that, just that notation on that graph. The graph didn't change, but the title of it should, right? This vertical axis represents the opposite of the cotangent of t. Where we do see that it does make this cycle twice, right, on this interval from 0 to 2 pi. One cycle occurs from 0 to pi, the other cycle from pi to 2 pi. And at pi and 2 pi, we have these vertical asymptotes. Those vertical asymptotes are where we have the vertical tangent lines to this parametric curve at the value of 0 and pi here. And then again at 2 pi. Right, 0 pi and 2 pi. At the values of pi over 2, which would occur here, and 3 pi over 2, which would occur here, we have that slope of the line tangent to the curve 0 in value. Those are the horizontals. And between this vertical asymptote and this location at 0, we're negative, and from where we're at 0 to this vertical asymptote, we turn positive. Right? That's describing the slopes in these two regions, respectively. Right? So, folks, parametric curves, right? For parametric curves, we can form descriptions of the slope of the line tangent to those curves. Those are still going to be described by the values of dy dx. However, in terms of their calculation, right, we are going to form the derivative of y with respect to t over the derivative of x with respect to t, and develop these descriptions of dy dx in terms of t. Where at any particular point in t, or for t, we can evaluate the slope on the curve using that formula, or analyze the functional behavior of dy dx in terms of t to come up with an overall description of those slopes of the lines tangent to the curve. All right? So, folks, that does complete this quick little bit of notes about parametric equations and their curves. I got one more idea to come back to in terms of finding the length of a parametric curve and some of the calculus involved there. So I will be back shortly with that video, folks. All right, folks, back here with the last bit of material that I want to cover with regards to parametric curves. And that's looking at this case for arc length, right? The case for arc length of a parametric curve. And we start off by considering the following set of parametric equations, that being this set, again, generically given by x equal to x of t, y equal to y of t, right? The length of this parametric curve described above over values of t in some closed interval from a to b is given by this calculation here, is given by this integral from a to b for what is the square root of the first derivatives of our components for the parametric curve squared, right? The sum of the first derivatives for these components squared, right? We need to take x prime of t, square it, and add it to y prime of t, square it, and place it underneath this radical symbol within this integration that occurs with respect to t from a to b, right? This is how we calculate the length of a parametric curve. If we consider an example, right? We might consider the length of the parametric curve described by this curve here, x equal to t, y equal to 1/2 t squared, for values of t in this interval from 0 to 1. All right? That would be a curve that's illustrated here as follows. Right? It is this small portion of this parabolic curve, starting down here at t equal to 0 and continuing up here to the value at t equal to 1. Right? What is the length of this curve? Right? Well, the length of that curve is given as follows. Now, you will notice we will need the derivatives of t and 1/2 t squared. The derivative of t is just 1. The derivative of 1/2 t squared is just t. So if I take those derivatives and square them, add them together, and put them underneath a radical, I will form the integrand in my integration. And that is the quantity I have right here. All right, where I'm now going to integrate this across values of t from 0 to 1. Now, you may recall that this integration is kind of in a unique form. This is an a squared plus a t squared form, or what we might say is an x squared form, a squared plus an x squared form, but now written in terms of t being the independent variable, right, underneath a square root symbol, where if you spend a moment and go back and think about how that's calculated, you could use either trigonometric substitution or spend a moment in the integration tables where you will see this result given for the antiderivative in the integration tables. Right? I did grab this from the integration tables. If I look up that table number, it would be table number 76 in our book. Right? Where if we evaluate that across the bounds from 0 to 1, one thing I will point out is that 0, all this quantity does 0 away. When you plug in 0 into this t, this will make this first term 0. When you plug in 0 into this inside of the ln argument, this will turn into the value of just 1. But the ln of 1 is also the value of 0. So you would have 0 plus 0 in value, which is nothing but 0. That's what we get when we evaluate this at 0. So really, we only have to concern ourselves with its value at 1. At 1, this will turn into the square root of 2 over 2, and this will turn into 1/2 the ln of 1 plus the root 2. We see that result given here, down below. So subtract from that the result we get at 0, which is nothing, right? And what you're left with is this argument here, right? Where if we approximate that, we put that into our calculator and come up with a decimal approximation. That is about 1.148 units in length. And that does seem appropriate. If we consider the length from here to here, it is certainly going to be greater than 1, right? The length from here to here is 1. This distance from here to here is certainly going to be greater than 1. And 1.148 seems like a reasonable approximation. It's not out of line by any means, right? If we consider another example, we might consider the length of this parametric curve, this circle, right? This circle in the plane whose center, right, or I should say whose parametric description is given by this, which indicates the center is at 2, 3, right? Its center would be right in here at 2, 3, and has a radius of 5, right? So it's 5 units away in all directions from this center. What would be the length of this curve starting at 0 and going all the way around to 2 pi? What's in a sense the circumference of this circle? Now, you could go back and rely on, right, your fundamental understanding of a circle, most certainly here. Their circumference is what? Pi r squared. R here is 5. Oh, careful there. Not circumference. Circumference is pi times the diameter, right? Where Our diameter is 10 units if our radius is 5, so times pi would be 10 pi units in length. Let's see if the parametric description here, its calculation of L using the calculation given above, gives us that 10 pi units in length. If we take note, x's first derivative up here is just going to be what? Negative 5 sine t. Y's first derivative will be 5 cosine t. And if we square those, we will get the square root of, well, if we square those, we'll get 25 cosine squared t plus 25 sine squared t. And if we drop that underneath a radical, right, we will build the integrand to this calculation given here. We will have the square root of 25 cosine squared t plus 25 sine squared t underneath this radical, which is being evaluated across these bounds of for t from 0 to 2 pi. Now, if you do take note of this value under the radical, you can factor the 25 out of each of these terms, leaving behind just this cosine squared t plus the sine squared t, where we know that that value is equivalent to 1 in value. So if we think about the value underneath the radical, that value underneath the radical is really just the square root of 25 times 1, or the square root of 25. Well, the square root of 25 is 5, so really we're just going to be integrating here the value of 5 across these bounds from 0 to 2 pi, where the antiderivative of 5 with respect to t is 5t, and evaluated across the bounds from 0 to 2 pi leaves us 10 pi minus 0. So in the end, we get that 10 pi units in length that we were expecting, that was given to us from the equation for the circumference of the circle, where circumference is nothing more than the diameter times pi. The corresponding calculation for arc length applied to this parametric description gives us the exact same length. All right? So we note that, that is again confirming this calculation as being appropriate. All right? If we get into just a little bit of proof, I always like to prove as much as I can. If I look at the proof here, right? This proof does build upon what we understand for arc length developed earlier in the semester. If you go back to when we presented arc length, I think it was back in chapter 6. I think section 6.5 is where we perhaps talked about arc length, right? Where in that formula for arc length, in that calculation, it developed from applying a limit of a Riemann sum to this quantity given here, where when we think about approximating the length of this region, it was the summation from k equals 1 to n for this calculation given here, where this calculation developed from just Pythagorean theorem, and delta x was a small incremental change in x, and delta y was a small incremental change in y. The square of those two small incremental changes added together and then taking the square root coming from the Pythagorean theorem would give me the incremental change over a kth subinterval of the length, where if we sum that up all over n subintervals of that length, we will obtain, right, the overall, an approximation of the overall length of value of L. All right? This is what we developed earlier in the semester for our approximation of L. Now what we can do here is bring delta t into this problem. How we get delta t into this problem, right? We take note that the argument above can be rewritten with a delta t if we just multiply that factor, this argument on the inside, this radical, by 1, right? Realize this delta t over delta t is just 1 in value, but we're going to multiply by 1 in the format of delta t over delta t. Now, the delta t in the numerator is going to hang out outside of the radical, right? Whereas this delta t seen in the denominator, it's going to move inside the radical. When it moves inside the radical, it will be squared, and then it'll distribute itself across those terms and become a term in the denominator of each of these quantities squared. If we do that, that will prepare this result here, right? Moving this delta t from the denominator into the radical, it will distribute to each of these terms as a square. So we can think of each of these terms as delta x over delta t quantity squared plus delta y over delta t quantity squared, with this other numerator aspect of delta t over delta t. This numerator up here left outside the radical. Where we know we can make then the value of L more exact, or actually make it exact, by applying the use of a limit. If we apply the use of a limit, right, the limit as n approaches infinity, we'll end up forming this exact value for L. L will be the limit of the summation given above, right? Where now from the definition of the definite integral, we know how to translate this statement. And from the definition of the definite integral, right, we recall the limit of the summation turns into the integration from a to b. The delta t is going to become our dt value, and the delta x over delta t and the delta y over delta t will become the dx dt and the dy dt seen down here in this result. Right? Where, what do we know about dx dt and dy dt? Well, dx dt is just x prime of t, and dy dt is just y prime of t. Right? And since dx dt is just x prime of t and dy dt is just y prime of t, we're able to rewrite L as this final statement. Right? Where this final statement of L illustrates our what? Our integral calculation for the arc length of the parametric curve described by x equal to x at t and y equal to y at t. Right? Here we have the proof of the given formula for arc length. Right, folks? So I did work through two quick examples here of this calculation and gave you a little bit of proof. Right? But all we are looking at in this section is calculating the arc length of parametric curves. And that is done through this integral calculation, right? Where you are going to have to set up the specific integrand by looking at the first derivatives of your components of the parametric curve, x at t and y at t. Take their first derivatives, right? X prime and y prime, square those, add them together, and put them underneath this radical. And then evaluate that radical's derivative, or sorry, integral across these bounds of t from a to b. All right? That will give you your arc length of that parametric curve over this interval of t. All right? So folks, that does finish my lecture here, my video lecture on parametric curves. I hope you're all doing well out there. I hope you're hanging in there. I have seen a few of you in the Collaborate, and I know that you're all have a test that should be coming in very soon if you haven't turned that in already, right, by the time you get to this video. So make sure that you're staying on top of your studies, because shortly your fourth test for the semester is going to roll up on you here, and then we certainly are going to still have our final exam. So make sure that you are staying on top of your studies. But other than that, folks, I hope you're all hanging in there and doing well, and I will be back in the next video. See y'all then.